let's dive into what Copernicus data space ecosystem is. Again, let me start with a quote from Thierry Breton, Commissioner for the Internal Market. When Copernicus data space ecosystem was launched, the whole talk was about data accessibility. At some point, we realized that making the data open and freely available on the internet is not enough, because then it's still only accessible to specialists who also own a big computer. And I think many of you guys know that specialists owning a big computer is just a small part of the world. We want to get the data out there to everybody in the real sense of the word. And this means we want to attract new users, and we want to move towards the non-space sectors. And our tool for this is cloud computing. So luckily, with the growth of cloud computing, you can do all the data processing on somebody else's computer. And this is what I want to show you. So data access, of course, starts with the data coming down from the satellite and being available on the ground station. And then it's stored in a server in just a typical way. And then we have the processing pipeline, the task of processing the data itself. What you see here is a time series of Stromboli volcano. There's also a custom script applied to it, which is highlighting the radiative power of the lava flows. So sometimes it turns yellow and red. That's not the actual color of the lava. It's a visualization of the power. But to create this visualization, we had to take the data from the servers. We had to put it in a common grid. We had to sample it into the right size. Then we had to apply an area of interest. We had to filter out the cloudy images. And then we had to apply this visualization and put the whole data into a GIF so that it's compatible with PowerPoint. This is, in a very brief nutshell, the typical Earth observation data analysis process. And so the concept of Copernicus data space ecosystem is to do this in the cloud, in our cloud. And then the next step is the visualization of data. So you have some sort of analysis, and then you want to turn it into a visual thing which is understandable for everyone. And again, in Copernicus data space ecosystem, the actual rendering, the calculation of the graphs is also taking place on the cloud. So you don't even have to download the result of your Earth observation calculation, because the visualization is also possible to do online. And then at this level, your computer is really just an interface. It's your way of communicating with the cloud, with the server. And so you don't need storage space, you don't need performance, you don't need a big machine. You can do it all. My happiest day as a PhD student was when I bought my first gamer laptop from Project Money. I was really, really pleased about that. We have to forget about this. Unless you have a very good reason to do local processing, there's no reason anymore to do satellite image analysis on a gamer laptop. You can do it on tablet or just maybe even your phone. So the arrows connecting these dots or these stages, that's the data infrastructure. That's the system that enables the processing to function. This is what Copernicus data space ecosystem is about. So Copernicus data space ecosystem has Sentinel data at its heart. And if you have already worked with the predecessor of CDSC, so Copernicus Open Science Hub, then you know that even this is not trivial, because Open Science Hub used to have the last 2 years of Sentinel data immediately available, and everything else was on a tape archive. You had to submit a request. You had to wait for it to be written to a zip file, and then it was sent to you for download. So this is gone. All the Sentinel data that have ever been collected over land are available in Copernicus data space ecosystem. And then we also had Copernicus contributing missions data and additional Earth observation data sets for complementing this. So we have a portfolio of open data that really enable you to create hardcore downstream applications. And then we have the APIs. So if the abbreviation API doesn't ring a bell for you, and it didn't for me when I started this job, it's application programming interface. It's essentially a machine-to-machine interface. It's a piece of code that runs on the server, which enables your machine to communicate with it. So you can write code in a way that it's going to create commands that run on the cloud. And this means that you can access data collections the same way as you access variables. When you say I equals 10 in your code, then later on you can call I as a variable, and it's going to mean 10, and you can calculate with it. And in the very same way, you can say, I want the pixel of Sentinel-2 on this date at this location and these bands. And you can operate with that in the same way as a variable. This is what APIs are for. So this is what we call streamlined data access. And Sentinel data and APIs together are powering Copernicus browser, which is our interactive web viewer, which we're going to explore in the next session. And in addition to Copernicus browser, we also had onboard folk repositories. Learning Earth observation coding used to be very, very hard. It was so hard that I didn't do it either. Because you have to understand a bit of photogrammetry, you have to understand a bit of geodesy, a bit of GIS, and then the whole thing in the computer. And Copernicus data space ecosystem is working really, really hard to make this a series of incremental steps to make it as easy as possible. So that's why we have code repositories, which you can use as learning tools, as building blocks, and then you can build your system together from the scheme of modules. And then we have cloud computing capacity. And cloud computing capacity, Sentinel data, and onboard code repositories together, I think this is really the transformative solution, having the code, the computing capacity, and the data in the very same place physically and on the cloud. This means that you can compute very fast, you can use the tools which are directly on board, and this really gives you a lot of opportunities. And these three, they meet in our online code labs. We have a Jupyter lab. We have a place where you can create a virtual machine for yourself, which already has the data there, and it already has the code repositories there. This is something we're also going to try in the hands-on. And then additionally, we have federation and user identity services. We can't make one data space to rule them all. That's not the purpose. We want to build an ecosystem, and this means we want other data spaces to accept our user identity or us to accept their identity. Have you heard of the European Open Science Cloud? It's a big repository of scientific open data. And we hope to federate with repositories like this in order to make sure that you can access that data and Sentinel data and work with it to put something together. And then we also have a traceability API. Oh, yes. So we have a system of making sure that satellite images cannot be altered or tampered with. We have a checksum in every image, and we have an API for checking the product of these images. And with that, you can verify that it's actually coming from the official source. So all these bubbles put together are what we call an open ecosystem. And as an ecologist, I really used to hate people saying ecosystem to a tourism ecosystem or an IT ecosystem, but this is a bit like it because, in a way, sunshine and photosynthesis are powering the whole thing. And here we have open data coming through regularly day by day and powering all these different systems and all these different players at various levels who are building on top of it. And we really hope that we will have more and more industry partners joining in and offering their services inside this ecosystem. Just to recap quickly about Sentinel data, we have all these satellites now, you know them all by heart, 1, 2, 3, 5B4, Sentinel-5 coming up, Sentinel-6. And the real challenge is to make an operational application that can be used day by day. This is the cap monitoring of Slovenia. So a hexagon is yellow if it has many uncertain parcels where they're not sure whether the farmer was doing the right thing. And it's green if all the parcels are confirmed to be correct. And as time progresses throughout the year, as the time series gets longer and longer, they collect more and more information about the crops. They are able to identify the cropping practices, and then the country goes from yellow to green. This is how cap monitoring can really solve the challenge. So Copernicus data space ecosystem is the source for Sentinel data. Anyone else who is sharing Sentinel data on the internet is getting it from us. So that also means this is the first place, the fastest place to access the data. And one of our our performance indicators is actually how fast we publish the data. We have to have rapid response times of 8 hours for certain data sets and 24 hours for most of them. At the moment, we have 80 petabytes, and we hope to have more than 100 petabytes by 2028. I think this is going to grow even faster. And we have a service level agreement. Right now, we have commitment until December 2028 that this is going to be there, and we will be the ones who can develop it. And depending on the next EU budget cycle, which is always a big deal, we hope for continuation for this project until 2032 and for the data space to go on for many more decades. And then we have this open ecosystem of different services. So again, once more to quickly recap the optical satellites, we have Sentinel-2 with 10-meter resolution and about 5 days revisits. We have Sentinel-3 with 300-meter resolution with 21 bands and daily revisits and also thermal imaging. And we have Sentinel-5B with 7 by 3.5 kilometer resolution, focusing on air pollution and daily revisits. And then we also have Sentinel-1, which is a radar satellite operating through clouds. Radar images are a bit different to interpret, and we're going to practice this as well. They are influenced by speckle, a specific kind of noise in the signal. They are more complex, but they are not obstructed by clouds, and they're also super pretty. So these are the data sets immediately available. Level 1, unprocessed data. Level 2, processed data. And in some cases, level 3, analysis-ready data sets, plus the contributing mission data sets and the elevation model. All this is open and free. Some of the expert data has restrictions. Expert data includes things like orbit parameters or unprocessed level 0 data. Some people want to do their own processing, and then they can access it, but this special conditions apply. I don't know how much you've heard about different levels of analysis-ready data. We are trying to prepare data in a way that you don't have to work with it. Analysis-ready data means that for a specific application, there's no more data preparation to work with. And it's a relatively recent thing that we have Sentinel-2 and Sentinel-1 mosaics in Copernicus data space ecosystem. Sentinel-2 mosaics are created once every quarter, so every 3 months. We take every cloud-free pixel and we calculate actually the first quartile, not the average, the first quartile of the distribution of pixel values. We do this to make sure that even if there's a single cloudy image in there, it's not going to move the average away too far. That's why we use the first quartile. These are seamless data sets, so no swath edges, no clouds, except in places where we've got like clouds every day for 3 months. That sometimes happens. It has RGB and near-infrared bands, so it's suitable for land cover classification and a bit of a benchmark for disaster monitoring. And these data sets are machine learning ready. So if you want to run high-level deep learning stack on the data sets, again, you don't have to prepare the data. It's immediately available in a consistent structure. And we also have Sentinel-1 monthly mosaics. They are one of my favorite data sets in CDSC. Terrain flattening is applied, which means that the effect of terrain from the side look angle is evened out. And these data sets are really, really clean because they have no swath edges. The speckle, the noise problems are really dramatically reduced. And again, these are really suitable for land cover and agriculture mapping. At the moment, the slide is already outdated. We have them all the way until August 2024. And so these are the cloudless mosaics. And now we also have some downstream products from the Copernicus services. So from Copernicus land services, we had vegetation products. This is the timing of the season peak as a product, already nearly a readily developed crop map, since different crops will have different seasonal peaks. We have snow and ice products such as snow wetness, ice cover, also a product of Copernicus land monitoring service. And we have the Sentinel auxiliary and engineering data, such as the health of the sensor, the attitude, the position of the satellite, again, for people who want to calculate something really, really fancy, sort of backwards. Moving on to CCM data. Yes, as I said, this is another CCM mosaic, the dyad mosaic of Naples and Vesuvius volcano with a near-infrared composite. So some of this is high-resolution optical data. We also have some high-resolution SAR data and digital elevation models. The whole idea is to complement analysis done by Sentinels with additional data sets here and there wherever you need it. And the additional Earth observation data sets, this is mainly the Copernicus digital elevation model, which is available for 30-meter resolution globally. This is the tandem XTEM, so created from a 2-satellite radar sensing configuration. But we also have ESMOS soil moisture, old MERIS data. Landsat is available in a specific way. Different Sentinel-1 products. So these are the additional data sets. Once more, what's the big difference between downloading a data set and accessing it with an API? If you want to download a data set, you're typically getting a zip, so a compressed product of a specific area. This is what you download. It's nice because you're not moving that much volume of data. In the predecessor of Copernicus data space ecosystem, we had this rolling archive approach. So current data was always accessible, but archive data had to be queried. And you are storing the raw data on your side, on the client side. Whatever you download is sitting there on your computer. Then you have to move it to a server or a virtual machine to process it. And this means, again, if you are thinking from the research or startup side, that first observation is going to be a heavy investment. Again, back in the old days, when I told my geophysicist friends that I want to work with Earth observation for ecology. They told me, I hope your thesis advisor has a lot of money, because you're going to start by buying a lot of disk space, and then you'll have to buy an expensive computer, and then you'll have to buy expensive software. And now this is what is going with CDSC. So the data is available for your area of interest, and the silver bullet for this is what's called the cloud optimized GeoTIFF. So it's a data storage format where you are not compressing the data at all. And this allows doing a spatial query without opening up the whole file. So you can subset the data, and you can deliver a small subset of the data immediately to the user without moving large volumes of data around. All data sets are immediately available. You're not storing raw data. You're just storing the very end product of your processing. And you can use virtual machines which already have the data on board. So again, you don't need to compare prices for different virtual machine services as long as you're not working at a very large volume. You can just use the free virtual machines in CDSC. And that means that you don't need that much investment. You can start growing your company or your research, and then you can scale it up if you want to go beyond the free quota later on when it's already functioning. Stack and OData and OpenSearch were the legacy APIs that were used in the era of the Copernicus Open Science Hub. So these are continued for backrows compatibility as well. These can query the data catalog. They can return a GeoJSON, so feature collections, and they are also suitable for downloading data products. But again, then you're only downloading that little bit of data that we actually want to work with. You can apply some filters. So these are working. We are expecting a new API prototype. Again, my presentation is outdated. Sorry for that. Hopefully by the end of this month, which will be really nicely compatible with the metadata. But what you really have to understand about APIs is that they come in different flavors, depending on what the end product is, right? So a catalog API is giving you a list of data sets. It's telling you which data sets are available for a specific time and place. Usually this is the first thing you start with, right? Give me a list of data. Visualization APIs with the OGC standard are returning a complete map. So something that you can put in a web interface or in GIS software. I think all of you have used the WMS before. That's one of the things that OGC APIs can create. We're going to look into this in a bit more detail in a moment. A process API is something that returns a raster product. So the product is an image, but you can already do the calculations on the server side. A statistical API, that's again massively reducing the volume of data you have to move, because you can calculate statistical operations within a raster vector integration system already on the cloud. If you have an area of interest and you want a time series of the mean NDVI, you can calculate through the API and you get the time series without ever opening an image. So that's what statistical APIs can do. And then a lot of people ask us, can I upload my drone image, my airborne image, my field data into this system? Yes, you can. If it's compatible with the cloud optimized GeoTIFF format, if you can bring it into that format using GDAL, then you can actually run the bring your own data API on it, and it's going to be put into a system that enables you to work with the same APIs. And then we have the OpenEO API family, which is a format and language independent scalable processing framework. You're going to see that in action as well in 2 days. So for catalog APIs, returning the list of images, we have OData, Stack, OpenSearch, and Sentinel Hub. And the new Stack catalog is coming up, which will enable a lot of different Stack API extensions. So this will allow you to look deeply into the metadata of the imagery. You can perform sorting operations. You can do filtering inside the Stack API, again, giving you only the data set that you need. This relies on a standard metadata model. This is actually the Stack metadata model is what powers this API. There are many different Stack compliant data catalogs out there from commercial providers, from various earth science data collections. And these are the systems that you can integrate using Stack. Then the OGC APIs allow you to create a web mapping service or a web coverage service. These are fully developed maps. So the OGC standard is used. The client computer queries a specific location and a specific layer, and then that's provided by the server in an already visualized manner. You can also do this for vectors. That's what the web feature service is about. But of course, we're mainly using raster data, so WMS, WNFTS are the tools we use. This even enables you actually to put Sentinel data on your smartphone mapping application if you're interested. I can show you in one of the breaks how to do that. It's not very difficult. And this is powering our QGIS plugin. So again, if you work a lot with QGIS, the Copernicus Data Space Ecosystem QGIS plugin is a really nice tool to use because it enables you to directly integrate and work with the images. Then we have the Process API. This is, again, our main workhorse. The output of a Process API request is a raster. So typically, you tell the Process API to perform some sort of spectral index calculation or even a small classification. Inside the API request, it's pulling the pixel values directly from the images. It's doing the calculation, and it's giving you the result. And we also have a Batch API, which enables you to run these processes in an asynchronous way over very large areas, and then the results are put into object storage, and the process runs when you are away. Statistical APIs, this is what we use for creating time series. In this case, this is a moisture index in the USA. You can really see it's 1 year, so you can see the seasons. So this integrates your area of interest with the statistics you want to provide and the satellite imagery, and it does the whole calculation as part of the API request. So again, no downloading, no opening of files. This is done on the server side. You can do many different kinds of statistics. You can do count ranges, quantiles, histograms, and the whole thing is also available again for asynchronous processing over a large set of parcels. Then we have the Bring Your Own Data API. This enables you to ingest data sets into the cloud and to work with different data sets which are not supplied by CDSC. What we have here is a test image from the Constellar satellite. This was high-resolution thermal imaging, and we used the Bring Your Own Cog API to ingest it into CDSC and to overlay it on a Sentinel-2 image. And then we have OpenEO. So OpenEO is a completely open code framework. It's developed by amateurs, but also by companies in the framework of an EU-funded project. And the idea is to provide an API which unifies access to Earth observation. So if you remember GDAL opens every data format and it exports to every data format. This is sort of the approach that they wanted to create with OpenEO, communicating with every data repository and giving you the results in the API processing framework. So it's very highly scalable. It works across many different platforms, many different backends, not just CDSC. And it's independent from many different underlying tools and software libraries, including coding languages. So it runs in Julia, JavaScript, Python, and R. And it even allows you to translate or to write one piece of the code in this language and another piece in that language, sort of module by module. So it's a super powerful system. And it's also very strongly designed with the approach of the FAIR, so findable, accessible, interoperable. I don't know what the third is, or what R stands for. So these principles of open science to make sure reproducible. Yes, that whatever you do in OpenEO is really open for other people to use. So it's an open source API system, focusing really on simplifying Earth observation analysis. And it's really combining these. So it works in a module structure through scripts in different languages. And it also has its own data cube system. A data cube is just an n-dimensional structure of spatial data, typically. And OpenEO has its own data cube format. This is a bit of a downside because then you have to ingest the data. But once it's in the OpenEO cube, you can do absolutely anything with it. Time series, spatial subsets, spectral subsets, without working with a specific data format stored on your computer. So this is really optimized for high-speed work. And you get different interfaces. So you can work with it. Oh yeah, it design which is JavaScript, Python, Jupyter, R, and it interfaces very closely with Copernicus Data Space Ecosystem. It has a web editor, so even a point-and-click graphical interface for those who are just learning this, but it also works in the Jupyter lab of CDSC or on your own computer. Oh yeah, and it has a data marketplace. So if you have created an OpenEO process, you can commercialize it or open it up within CDSC for other people to experiment with it or to actually work with it in a commercial way. So we have all these APIs. Copernicus browser is a visualization tool. And again, one of the limitations that people experienced with Copernicus data was that it's not so easy to look at. And then if you remember the Sentinel Hub EO browser, that was a free tool that many people use just for for looking at Sentinel imagery because it ran in a simple web browser. And what actually happened was that the commission, when they designed Copernicus data space ecosystem, they approached us to create a free version of the EO browser. So this is Copernicus browser. It uses most of the same tools that EO browser uses, and it's a really, really easy system to work with. Let me give you a very short animation. We are in the Canary Islands. We are trying to look at the effect of volcanic eruption. You can see that you can also create 3D view of the volcano. And this is the lava flow, the sign of the damage done by volcano. So if we exit the 3D view, we can also look at the process as it happened in time. So now we are creating a time lapse. Don't worry, we're going to do this hands-on as well. So we have queried using the API again, the catalog API, and created thumbnails of all the images to find the one where the eruption is actually happening. And then you can scroll through different visualization indices to find the one that's really highlighting the radiative power of the eruption. Again, quite nice in 3D. And then what we want to do is the before and after comparison to actually quantify the area affected by the lava flow. So this is the LDVI. We take an image before, we take an image after, and we add them to compare view, and then you can really, really see the effect of the volcano. So it's as fast as this. Anybody can really do small-scale analysis on Copernicus browser. It's also a tool for downloading individual images or individual image tiles. Normally, you wouldn't want to download an image. I still keep trying to convince people to not download imagery. But if you need to do it for whatever reason and you want a single image from a specific place, then Copernicus browser is the place to go. The most important functionality of it is really interactive visualization and analysis, but it's also useful for time series or for histogram mapping. A lot of the statistical API functionality is there in Copernicus browser. And of course, you can create really nice and compelling images, which you can also export and put on your bedroom wall. A couple of new functionalities. It's now integrating Copernicus elevation models, and it also allows you actually to calculate elevation profiles. We have the spectral explorer, which we're going to look into in really high detail. So for a specific point or a specific area of interest, you can actually look at the optical spectrum of Sentinel-2 data, and you can compare it to reference spectra to find out what your land cover is. This is the elevation profile tool just in a place in Norway. And we have themes and highlights, those small tagged places for exploring that people can look through individually to explore the browser. And then we have the custom script repository. All these visualizations that are done in Copernicus browser run through a small piece of code. Essentially, you have the backend doing the heavy lifting of handling all that data. You have the front end, which is doing the visualization. And the little bit in between, the actual task of processing the data and visualizing the results, can be handled with a small bit of code. And we have an open user contributed repository for these spectral indices and these custom scripts. And that's really handy because many of the things that you would want to do with Earth observation are already there. We have our code labs. So we have the Jupyter lab, which is a small virtual machine thing that runs inside the data space. It already has the dependencies pre-installed, such as Sentinel Hub and OpenEO and OData. And we have a lot of tutorial notebooks that we're also going to work through. OpenEO has this graphical interface. Sentinel Hub also has a graphical interface called Requests Builder, something we're going to look at as well. And I hope we move over to cloud computing capacity. Yeah, let me give you a use case example. This is Epsilon, a German company who are looking at yield forecasting, and they are creating high-resolution crop yield models across the whole territory of Germany. So a really data-heavy thing. And behind this, they have a biophysical model and also a very strong deep learning system. And they're integrating meteorological data and Sentinel-2. So the platform they use is, of course, Copernicus data space ecosystem on the Open Telecom Cloud. They are creating this service based on our cluster. And this takes, it pre-corrects the images, it does a land use classification, and then it calculates the cloud parameters. So these guys can actually do their European level services without downloading individual images or without operating their own servers back inside the data space. Open data and open processing is always sort of balancing on the border between commercial and open. So often you have a public company who are subcontracting a private company to do something which is a public service, like cap monitoring or disaster monitoring. You are paying them, so they are using their own algorithms, but the results still have to be public. Or you have somebody in a research project developing something. It's proprietary, it's their own stuff, but then in the end, they want to create an open repository of it. And so we really tried to make it easy to move from open to commercial and back. And the tools for this, we have the commercial part of Copernicus Data Space Ecosystem, Cloudias and our other third-party cloud providers, and they are running the same stack, which means you can use the same code, you can access the same data collections. And so your code, which you have developed in the open system, can also run in the commercial system, or something that you found in the commercial system can also be opened in the open cloud. So this is the way we are really trying to make it easy to move between commercial and public. Just very quickly, I'll flick through the commercial element of CDSC. This is Cloudias. So this is a data processing platform, a virtual machine provider, who are also hosting the Sentinel data on their physical cloud. And they also have the Jupyter library or the Jupyter lab in the very same way, so that you can work with the data the way you've developed it in CDSC. Again, just a little example of what you can do here. This is monitoring of glacial change in Switzerland using the normalized differential snow index. This was run on the Cloudias cloud again and again, and then they ended up with this not very positive map. In Open Telecom Cloud, which is another cloud provider inside CDSC, there's a pre-designed AI stack. So they're not just giving you a virtual machine, they're actually giving you a lot of the libraries, the GPU services, the dependencies, so that you can actually take care of the part you like to do, the Earth observation coding or the application for yourself. Slowly coming to an end. Yeah, the future, of course. So Copernicus Data Space Ecosystem is going to post the Sentinel expansion missions. And I didn't talk too much about these in the Copernicus program presentation. But of course, the Sentinel satellites are also receiving some upgrades. Nobody said that we can't make them better, right? So in the near future, Sentinel expansion missions are planned, which are giving even higher resolution. They are focusing on specific biodiversity-relevant applications, climate-relevant applications. And of course, these data sets are also going to be shared in Copernicus Data Space Ecosystem. But with this federation approach, we really hope that commercial providers are also going to serve their data through Cloudias inside CDSC, and then we can be sort of a publicly owned data marketplace. A lot of commercial providers are sort of shying away from sharing their data in an infrastructure which is not their own, right? Airbus is using the Airbus cloud, Planet is using the Planet cloud, and Sentinel is using this public cloud. But we hope that if this is a public marketplace, it's not owned by a market player, then they should hopefully open up to also sharing their data inside this infrastructure, and that's going to make data accessible for everybody. And then, again, we are hoping for a lot of downstream applications, and these should also be both on the public and the commercial side to be designed based on Copernicus Data Space Ecosystem. So using our platform, our virtual machines, our APIs, I think that a lot of these services can be set up both on the commercial and on the open side. And finally, our big hope is also federation. So again, both on the public and the commercial side, there's all these different data spaces, data processing infrastructures with cloud capacity, which we could connect to. And using our APIs, if they are compatible with the structure of other data spaces, it could really be possible to break the boundaries of data storage and make very highly interoperable systems. So, well, what we need from you guys is to build the bricks, the building blocks for all this. And these are many different things. It could be a data set, it could be a custom script, it could be an algorithm, it could be an error report, but everything that you can build is really contributing to improving this whole system. And because it's a big open platform, we also hope it's a very strong platform for collaboration between people. Again, you're not locking yourself into a specific vendor or a specific GIS software. You can use the open system, which everybody accesses. Upcoming developments. We are now at Q4 2024. So Landsat data is coming, hopefully including visualization of Landsat data in Copernicus browser before the end of the year. Our new Stack API is coming. And Sentinel-2 has been reprocessed right from the start with the standards of collection 1. This is already available in the dataset. Let me brag a bit about our user counts. We are in the 100,000s. So at the moment, we have something like 200 to 300,000 registered users. We had a big peak of data usage in April. Way above 100,000 people were using Copernicus browser within a week. And this is what we actually care the most about, streamlined data access requests, because this is API requests, people building code that runs and accesses the data and creates data processing on the cloud using our tools. And this is also really, really nicely growing. Not just the process API usage, but these analytic tools, which are more related to commercial applications. So I think that Copernicus data space ecosystem actually solves the problem of accessing Earth observation data. Earth observation data was difficult because it was big, because it was hidden in different places. We are now bringing it together and really, really making it easy and analysis ready, depending on what analysis ready actually means to you. Data processing, again, a difficult thing because you need big infrastructure for that. But now we have the cloud. We can do petabyte scale processing, and you're going to do it on your computer in a very, very short time. And it's also very easy to learn this now because of these different code repos. So it's not something only specialists can do, but it's really available to everyone. And data sharing, again, a challenge. I've created something. How can I get someone else to use it? If they have the same platform, if they have the same kind of data storage, if they have the same software, right? But now that we have the data space, it's really possible to share algorithms in a very, very easy way and make it interoperable for everyone. I'm concluding with this slide. This is, again, a result of a survey done by the European Association of Remote Sensing Companies. The question to European companies and public authorities was, what platform do you use for accessing Sentinel data? And now the biggest piece of the cake is finally Copernicus data space ecosystem. And Sentinel Hub has the same share, but Sentinel Hub is part of Copernicus data space ecosystem. So it's really, these two are both CDSE things. And we are finally growing and providing this data set for everyone. A transformative solution is something that's bigger than the sum of its parts, that really breaks boundaries and enables a new way of working. And I think that Copernicus data space ecosystem is a transformative solution. Yes, we are using GitHub. Actually, the front-end code of Copernicus browser is on GitHub. Our tutorial notebooks are on GitHub. So GitHub is the typical thing that we use for sharing. Then we have version eval. The browser can give you NDVI directly, and you can also calculate it as part of an API request, and then you have it direct. It has to be in a stack compliant repository, but then OpenEO can access it. The bring your own COG API is part of Sentinel Hub, not OpenEO. And then again, if you put it into object storage on CDSC or CloudES or on AWS or somewhere where the system can access it, then you can convert it to a cloud optimized JOTIF and ingest.
Then we will be able to cooperate with this engine.
Yes, you can then use the very same tools to work on it. You can even load it in the browser. It depends on the area or the ratio that specific plant is covering within the pixel. I mean, if it's very tightly planted and covering the whole area because it's a farmed field, then of course it's going to dominate the spectral signature. If it's a bit of a noisy pixel on the edge of the field, or you have a mixing between one land cover class or the other, then not necessarily. Yes, that's being done as we speak, of course. That's part of cat monitoring, yes. Yes. Actually, Hungarian cat monitoring works with 22 vegetation classes, which are calculated with a random forest classifier based on time series of Sentinel-2.
And I have a question. You were mentioning the data cubes, but you didn't mention the Eurodata cube. And I'm pointing this out because the Danube data cube that we will deal with on Friday is also linked to this system. How should we imagine this? That what are these data cubes doing, and why it was not mentioned there?
They are federated systems. So when I talked about one data space connecting to another data space, people can build their own application on top of Copernicus data space ecosystem, where they create a piece of code that do specific processing tasks. So in case of Danube Data Cube, this is a set of code modules specific to agriculture, yield monitoring, crop forecasting, crop identification. And then in the backend, it's running using the code tools, the APIs of Sentinel Hub and CDSE. But they have created an additional processing level on top of this, and they are opening that towards the market and serving it. So this is one way federation works. It could be only data level federation, like you can access the data set, but you work with it with your own tools. But it's also, I mean, code level federation is also available, where somebody is building something that's using the APIs and then building on top of it.
Yeah, so that's why I was asking this simply to see the relation between this first part of the course with the last half day, Friday morning. We will focus on the Danube Data Cube.
Yes, I have a couple of more technical questions online. Whether the presentations will be shared and the recording is going to be shared, yes is the answer to both. And the GitHub profile, we will, during the course of the workshop, we will share links to several different GitHub repos where you can start working with. But it's also available in the documentation. So if you go to the documentation site on the CDSE page, then you can find your way to the GitHub repo. We have a really nice question. How would you compare this data space with Google Earth Engine? It's always difficult to compare a public service with a commercial service because they have different goals. And of course, I'm in favor of CDSE very heavily. But let me give you a story here. I was looking, I had the task of creating a satellite image from palm oil plantations in Borneo, but I don't know what a palm oil plantation looks like on a satellite image. So I found a paper published in Nature Communications about a global scale map of palm oil plantations. And they also said there's an online map and an interactive data set with this. And so I opened up the paper, I clicked the link, and it was to Google Earth Engine, and it was not working. And we had the same thing. We created, me and a couple of my friends actually, as a hobby project, we created a global water quality viewer as a combination of Google Earth Engine applications. And it worked really beautifully in Google Earth Engine. We hope that this would grow. But what happened was that Google changed something in the backend because, they have no obligation to not do that. And then my developers didn't have the capacity to follow up and to make 2 lines of code different. And then the system was broken. So the problem with Google Earth Engine is that it's not governed by a service level agreement. When you use it, you don't sign, you sign an agreement with Google, but that's not a commitment of them providing a specific service. And so if they make a change, there's nobody to hold accountable. And often this means that you can lose functionality. But they also have APIs, so they also enable cloud processing on their cloud with their system. And it has created some of the most used Earth observation applications in the world. So big contribution to EO. And I hope we are overtaking them now with CDSE. More questions?
And so I have a question on top of that, because the Google Earth Engine has a limitation on processing the free clear.
Yes.
So when here in the opening and free access site, do we have any limitation? Never 10,000 points to extract, because the Google Earth Engine, you can extract around, let's say, 2,000-3,000, no, maximum 5,000 points. And then after that, they said, otherwise you reach the machine unit.
It's calculated a bit differently because we actually use processing units. So the processor time in creating the API request, not so easy to illustrate. You get 40,000 processing units. When you are creating a time lapse, like what you saw with the volcano, one image like that is one processing unit because it's an RGB image of 512 by 512 pixels. That's one processing unit. Or the complete satellite-based cap monitoring of Hungary is running with one single free tier using. So you can do operational large-scale, national-scale application with high-level data analysis using the free tier. It's big. It's designed in a way that it enables somebody to launch a commercial application. And then if it's really growing and and bringing in money, then they can shift to Cloud.ES and buy additional processing units. And OpenEO, the OpenEO free tier is even larger than the Sentinel Hub free tier is. It's nearly double the size. So it's worth experimenting with. Another question in the Q&A, whether there are restrictions to commercial use of the ecosystem. Not really. The only restriction is for Copernicus contributing missions data, but anything else. So if you're developing a company or you're creating some revenue, there's no restriction to the data or the processing inside CDSC. So the processing quota is not just for free or scientific users or non-profit users. You can also use it for profit specifically.